I pulled this up related to the conversation we had in the last lecture about the proof of concept for the ocean color. And the paper that I was talking about was this paper by Clark, Ewing, and Lorenzen from 1970, which preceded the coastal zone color scanner. And what they did is they had an aircraft, and they measured the upwelling light, which they called the backscattering light from the sea. And so they picked one spot, and they flew over it at a variety of different altitudes, and saw that the percent of light increased as you went up in altitude. And so that talked about like how much contribution was coming from the atmosphere over, because the water underneath it is staying the same. And then they went and they looked at how that spectrum changed for a variety of different waters from the Sargasso Sea up to Georges Bank. And so these are the graphs that are essentially the reflectance spectrum. And I can't remember the height that this was measured at. It probably says 305 meters above the surface. And so spectrum A, the chlorophyll, was really clear water, and it was less than 1 milligram per meter cubed. And then Georges Bank, or Georges Shoals, you can see that the spectrum is much greener, and there's a lot more offset in the red due to scattering, but that's for a chlorophyll of 3. And so this was demonstrating the change in the color of the water dependent upon chlorophyll concentration. And that was used to justify the development of the coastal zone color scanner, knowing full well that 90% of the signal that the satellite sees, at least, comes from the atmosphere. The fact that despite that, you can see these changes, because the differences in shape here, these are mostly similar shapes, but different magnitudes. And so the point was, if you could see the changes in the shape of the spectrum, that you should be able to get chlorophyll. So it was really, it's really amazing and that they were able to do this proof of concept. And so when I started graduate school, Carl Lorenzen was basically in his last few years and at University of Washington. But I was just like, oh my gosh, he's the one who helped justify ocean color. So it's a good read for a sense of history and to recognize that, we're talking about variability in the shape of these curves. We're still talking about the same stuff that they were talking about in the 70s. So, okay. So anyway, so this is the part 2 to Kurt's lecture about inversions. And so we're going to talk about semi-analytic models to obtain inherent optical properties from reflectance. So we can talk about this forward model. And this is what you've been spending your week on, is the forward model. And so you start with radiance and you propagate it through the medium, knowing the inherent optical properties that you prescribe, and hopefully you've checked your data, right? And then you use some radiative transfer equation like hydrolite, which you're doing this weekend, or Monte Carlo, which I think you're going to do in the 4th week. And you predict the remote sensing reflectance. So it's a sense, this is from a nice diagram by Bourne and Huffman, where you start with the dragon and you know what sort of tracks, you figure out what the tracks are going to look like, right? You can look at the dragon, look at his feet, figure out what the tracks are. The inverse model is where you start with some approximations to the radiative transfer equation, and then you use that to estimate something about the inherent optical properties. And you can use the empirical models, which Kurt just talked to you about, or you can use these semi-analytic models. And so if we start with reflectance, with the goal of deriving the IOPs, that generated the light field. And so that's analogous to seeing the tracks and trying to figure out what made them, right? So this is what we're going to do. So in 2006, one of the IOCCG reports came out, and it's on the remote sensing of inherent optical properties, the fundamentals, the test of the algorithms, and the applications. And Zhongping Li was the editor of that, and a number of people here all contributed to this report. And so in the first chapter, which is written by Ron Zanefeld and Andrew Barnard and Zhongping Li, they talk about this diagram of inverse radiative transfer and thinking about the black box approach, which is the approach that we just talked about, the band ratio, the neural network, where you start with the radiance, the spectral radiance, and you derive things like chlorophyll production or particle concentration. And you can think of this as being this nice band ratio here. And so you can estimate chlorophyll from radiance, but you're not really sure all of the things that lead to it and why there's so much variability in the y direction and so much variability in the x direction. But the thing that's important to recognize is that it isn't chlorophyll that's impacting radiances, right? Chlorophyll is our proxy for a lot of things. So chlorophyll is our proxy for phytoplankton absorption. Chlorophyll is often our proxy for non-algal particles because they might be particulate matter that's derived from phytoplankton production. Chlorophyll has been used as a proxy for particle scattering or backscattering because if you've got more algae in the water, you probably have a more concentrated ecosystem, and there'll be more detritus, there'll be more bacterial, there'll be more zooplankton, there'll be more products of all of those. And so chlorophyll becomes the proxy for a lot of things. But it's not the thing that is actually impacting. It isn't particle scattering, and it isn't phytoplankton absorption. There are many other pigments that absorb that aren't chlorophyll. So it's really the inherent optical properties that are changing the radiances. And so really it's the fact that you have particles of a certain size, an index of refraction, a size distribution, the property of dissolved material, the absorptive and scattering properties. That's what's impacting the absorption and scattering properties, and it's that's impacting the radiance. And so really what we should be thinking about is this, and not so much just chlorophyll. Okay. So they describe this, this process by which you start with the radiance distribution, or say the reflectance. You derive by inversion the inherent optical properties, the absorption, the backscattering. And you can derive the properties of, say, the absorption by dissolved matter, or absorption by particles, or scattering, backscattering by particles, or absorption, backscattering by water. You derive those constituents from the absorption and backscattering. And then, say, the particulates, you can divide it into organic and inorganic. You could divide the organic into non-living and phytoplankton and bacteria and viruses. You could divide the phytoplankton into accessory pigments and chlorophyll. And that is what's in your black box. That all of these steps are in that black box. And so when you think about it that way, it's not surprising that when you look at the OC algorithms, that there's a very large variability in the y direction and a very large variability in the x direction. And what's encompassed in there are all of these relationships as to why a certain band ratio is related to chlorophyll, because all of these other things are varying. Okay, is that clear? All right. So if we take sort of a heuristic approach to reflectance inversion, I want you to consider an ocean, and we did this at the beginning, but comprised solely of absorption material. And so I want you to think of a CDOM ocean. How would the reflectance depend on the absorption? So there's water. So we have the scattering by water. What's going to happen to the reflectance spectrum as we add CDOM? You'll get lower reflectance because you're increasing absorption, right? So it's going to get darker, right? The ocean will get darker as you add CDOM. What else will happen? It will shift to the red. The ocean will start off blue, and it will shift through the green into the yellow, and ultimately it can shift to the red, depending upon how much CDOM you have. Right? So absorption, if you hold everything else constant, darkens the reflectance, and depending upon the absorption spectrum, changes the color of the reflectance. Okay? All right, so now let's think about an ocean that's comprised solely of scattering material. You can think of a coccolithophore bloom or glacial sediments, and you have water, so water absorption comes into play. How does reflectance depend upon the backscattering as you increase the concentration of the scatterers? It's going to increase. Okay, is it going to change the color? I see no, I see yes. It depends on the particle size. So if you had big particles, it will be a white scatterer with big particles, so you'll just be amping up all parts of the spectrum in general. If you have small particles, or even blue, right? If you've got a particle scattering that looks like this, you'll be ramping up the blue part. So you could get a bluer spectrum just by increasing the concentration of small particles, right? So backscattering adding backscatters brightens the spectrum, but it can change the color of the spectrum. And you did some of those simulations yesterday with hydrolite, right? Okay, so the real ocean is comprised of some combination of absorption and backscattering material. And so we have to think about how reflectance depends upon absorption and backscattering. And think about the source of that upward radiance divided by the loss. So that's how we're going to approach this. So I want to start with, I have like 2 slides on this because I think Kurt's not going to do it, so I'm not going to derive it, but I just want you to think heuristically about it. So here's some history. We used to have this joke about the Howard Gordon Ocean, where the water's homogeneous, all the geometry was plane parallel, you have a level surface, the sun is a point in a black sky, and there's no fluorescence or Raman. And so there's your radiative transfer equation. And I think you spent Tuesday talking about radiative transfer equation with Kurt. So there's one approach to solving the radiative transfer equation, and it's called successive order scattering. And so basically what it does is it takes the radiance and it divides it up into radiance that propagates and is not scattered. So it goes from one depth to the other, and it doesn't get scattered. Okay. Then you can look at the radiance that gets scattered once within that layer, so one scattering event. Okay. Doubly scattered up until multiple scattering. So you can divide this equation up into those terms. The single scattering approximation is that, although now you have this big mess, right? Because each one of those terms has multiple terms in it. If you take only the unscattered light, so light that's propagating, unscattered, and the radiance that's been singly scattered, so just the L0 and L1 terms, and you throw everything else out. Now you can do the third approximation, which is the quasi-single scattering. And so that approach says that the volume scattering function is highly peaked in the forward direction. So if light's coming down, it interacts with a particle, most of the scattering is in the forward direction. And so light propagating down that's unscattered continues to propagate down. Light that's scattering in a single scattering, if it scatters in the forward direction, it's essentially lost. It never makes it into the upward field. Right? And we've ignored all the multiple scattering. So light propagates through, or it propagates to a particle, gets scattered down. So what that says is that any part of the radiance that's scattered is scattered in the forward direction. It's as if it wasn't scattered at all, because you never see it in the upward light field.